Welcome dear learners to this video for BSc second year 5th semester. In this video we are going to discuss physical properties and molecular structure part first. This is the content of this video. In this video we are going to discuss three important properties, in that first optical activity and its measurement, second dipole moment and its measurement by temperature change method, then magnetic property and its measurement by gauge balance method, application of optical activity, dipole moment and magnetic property for the determination of structure of a molecule. So let us start with first physical properties and molecular structures. All properties of the matter are either physical or chemical, and physical properties are either intensive and extensive. So these are the some terms related to these properties: physical property, chemical property. So a property of an substance can be broadly divided into two types: physical and chemical properties. And in thermodynamics, we have also divided properties into two types: intensive property and extensive property. So let us discuss first what is meant by physical properties. Physical properties are the properties that can be measured or observed without changing the chemical nature of the substance. Physical property is related to the physical change. So we can explain in other words such as physical property that is related to physical change. And some example of physical properties are color, density, volume, mass, boiling point, melting point, molar refraction, surface tension, optical rotation, dipole moment, and magnetic susceptibility, etc. Now let us discuss second important property, that is called as chemical property. Chemical properties are the properties that can be measured or observed by changing the chemical nature of the substance, or it can be defined as the property related to chemical change. Some examples of chemical properties are heat of the reaction or heat of the combustion. So it is clear now, it is clear that physical property related to physical change, chemical property is related to chemical change, and the examples we have already discussed. Now question arises, what is meant by physical change and what is meant by chemical change. So first discuss what is meant by physical change. So physical change is a change during which the chemical composition of the substance does not changes. And the example of physical change are melting, vaporization, boiling, etc. So during melting, during vaporization, or during boiling, the physical composition or the chemical composition does not changes. Suppose consider the melting of the ice into water, or conversion of water into water vapor. So these all are the physical change. That means ice is converted into liquid, liquid is converted into vapor. So in all these composition, in all these physical state, the chemical composition is same. Okay, the chemical composition does not changes. That is called as physical change. Now next point is a chemical change. Chemical change is the change during which the chemical composition of the substance changes. Okay, so example of chemical changes are chemical reactions, cooking, burning, rusting, etc. So during burning, the chemical composition changes. During rusting, chemical composition also changes. Suppose consider the rusting of iron. So initially, the chemical composition of the substance is Fe, that is iron, and after rusting, it get converted into iron oxide, FeO2. Okay, so that means during rusting, during burning, the chemical composition changes. Therefore, it is a chemical change. Now it is clear. You can easily identify what is a chemical change and what is a physical change. Now we discuss one more aspects of classification of physical properties. It is from thermodynamics point of view. So in thermodynamics, physical properties are classified into two important types: intensive and extensive. Let us discuss first what is intensive property. Intensive property does not depend on amount of substance present in the system. And you know that system is a part that is under our considerations. Now, example of intensive properties are color, density, boiling point, melting point, etc. Now, uh, I will elaborate this what is meant by intensive property. So here, if you consider the color of a 1 gram of a substance and the color of 5 gram of same substance, color does not changes. Similarly, density does not changes, boiling point does not changes. So all these properties, they are independent of amount present in the system. Therefore, these properties are considered as a intensive property. What is meant by extensive property? Extensive property depend on amount of substance present in the system. As the amount changes, the magnitude of this property also changes. Consider the example of volume and masses. Okay, so as the amount increases, volume increases, mass increases. So mass and volume are the important extensive property whose magnitude changes as the amount changes. Now, again, we can divide property in terms of two types, additive and constitutive property. An additive property is defined as a property whose aggregate value is sum of values of all its constituents. While a constitutive property is defined as a property which depend on the constitution or structure of the molecule, like arrangement of atom within the molecule, multiple bonds and rings. Suppose a matter is consist of four different particles whose properties can be x1 plus x2 plus x3 plus x4 respectively. Then in case of additive property, the net additive property is the sum of the properties of each and every constituent, that is x1 plus x2 plus x3 plus x4. Okay, in this way additive property can be defined. And constitutive property is a property which is depend on only the constituent of the structure. Okay, it is not a sum or addition of the property of individual particle. Now, this is in this way the basic concept related to the property in terms of physical property, chemical property we have discussed. Now we are going to discuss the first physical property that is included in our syllabus, that is optical activity. The ability of a substance to rotate the plane polarized light passing through it is called the optical activity. The intensity of optical activity is expressed in terms of the quantity, that is called as specific optical rotations. So if you want to compare the optical rotation of a different substance, then a term is introduced that is called as specific optical rotation. Louis Pasteur is well known for pasteurization process that is used for the preservation of the milk. But this Louis Pasteur is also considered as a father of organic stereochemistry because he first recognized the optical activity in organic compound. Optical rotation is a property of the substance to rotate the plane of the plane polarized light when linearly polarized light passes through the solution of the substance. This property is shown by optically active substances. Only the optically active substance have ability to rotate the plane of plane polarized light. And the rotation of the plane polarized light may be in clockwise direction or anti-clockwise direction. So if the optical rotation is clockwise direction, then it is a dextrorotatory, and if it is in anti-clockwise direction, it is called as levorotatory substances, or it is called as levo rotations. Okay, so we have two types of rotation of the plane polarized light, either in clockwise direction or in anti-clockwise directions. Now there are measurement, how the measurement of optical activity is done. An instrument is used for the measurement of optical activity, optical rotation, that is called as polarimeter. Polarimeter used to measure the angle of rotation. Now, polarimeter consists of different components. Before that, see here, this is the schematic diagram which is used to explain the instrumentation of a typical polarimeter. It consists of a source that is called as a source of light, ordinary source of light. When it is passing through a prism that is called as Nicol prism, then the emerging light have vibration only in one plane. If the light is having vibration in one plane, that is called as plane polarized light. In this case, light is having vibration in all possible direction, that is called as ordinary light. So ordinary light is having vibration in all possible direction, while plane polarized light have vibration only in one plane. So when such plane polarized light is allowed to pass through a sample tube containing a sample, if it rotates the plane polarized light either in clockwise direction or in anti-clockwise direction, then that substance is called as optically active substance because it has rotated the plane polarized light. Okay, so this is a simple idea behind this property that is called as optical activity. Now we discuss this instrumentation. First, the light source. Sodium vapor lamp is used, which produce a monochromatic light of wavelength 589 nanometer. That is the first source of light, the first component of a polarimeter. Second component is Nicol prism, which is used to convert ordinary light into plane polarized light. So specially made prism consisting of two optical pure calcite crystal made up of nickel and cobalt. So NiCO, NiCO or Nicol. This term Nicol is originated from nickel and cobalt. The combination of nickel and cobalt is Nicol. This will convert ordinary light into plane polarized light. That is the function of their Nicol prism. Then sample tube, also called as sample cell, made up of glass whose diameter is fixed. Specific optical rotation. The angle of rotated plane of polarization is called as optical rotation. Polarimeter is the instrument used to measure optical rotation. Optical rotation depend on different parameters such as path length of sample tube, sample concentration, measurement, wavelength, and temperature. So the specific optical rotation is used to compare the optical rotation power of different substances. So the specific optical rotation is calculated from the following formula using temperature, wavelength, cell path that is 1 decimeter, sample concentration that is grams per 100 ml, and measure optical rotation. So optical rotation is written here, alpha is optical rotation, and inside this bracket, that is if it is written inside the bracket and there are suffix and prefixes such as x and t, then it is called as specific optical rotation, where this t denotes the temperature at which the measurement is done and x denote the wavelength that is used for the measurement. So this entire term is called as specific optical rotation, and specific optical rotation is equal to 100 into alpha divided by c into L. Or in terms of when many times instead of x, this d notation is used. D notation means the d wavelength emitted from sodium vapor lamp. So specific optical rotation in this case is equal to 100 into alpha. Alpha is optical rotation, observed optical rotation, divided by C into L. C is concentration and L is the path length of your sample tube. Now there are various pharmacopoeia, JP, USP, EP, suggest that the optical rotation must be measured by using the D line of sodium vapor lamp. Okay, so this is all about a specific optical rotation and its measurement. Now, application of optical rotation or polarimeter. Polarimeter is widely used in food, agriculture, and pharmaceutical industries for testing purposes. So, the purity of the substances in agriculture, food, or pharmaceutical industries can be measured if your substance, if your sample is optically active, then With the help of polarimeter, we can make some prediction about the purity of that sample. The angle of rotation is used to identify the compound because it is a characteristic physical property. Therefore, it can be used for the identification. It also helps us to predict the purity of the sample. It can also be used to indicate the progress of the reaction and the conversion. The progress of the reaction can be measured with the help of this polarimeter, because if your reaction is going on, then the optical rotation of the sample after some interval is measured, and if your reaction is completed, then you get that particular value of optical rotation that indicate that the reaction is completed. Polarimeter are used in a wide range of applications, from the determination of purity and concentration of ingredients in pharmaceutical testing of agricultural products to the measurement of sugar content in beverage and candies. Particularly, polarimeter is very commonly used in sugar industry to measure the purity of the sugar formed during the process. Now we are going to discuss the second important physical property, that is called as dipole moment. Di name itself indicate di means two, poles means end. A dipole moment arises in any system in which there is a separation of charges. They can therefore arise in ionic as well as in covalent bond. So dipole moment is present in both ionic and covalent bond. Only important concept is that there must be some differences in electronegativity. Dipole moment arises due to the difference in electronegativity between two chemically bonded atoms. Dipole moment is a measure of the polarity of a chemical bond between two atoms in a molecule. Dipole moment is a vector quantity because both magnitude as well as directions are necessary for describing the dipole moment. Direction of dipole is oriented towards electronegative atom, and it is shown by an arrow pointing towards the electronegative atom. Let us consider this example. See here we have a two particle or two atoms forming a bond. One is having positive charge, another is having negative charge, and it is separated by the distance r. So distance of separation between these two charged particles is r. Therefore, dipole moment mu is equal to q into r. Q is a charge separation and r is the distance between them. So dipole moment is nothing but the product of charge into distance of separation between them. Now, dipole moment is the product of the magnitude of the charge and the distance between them. It is already defined. It is denoted by Greek letter mu, and mathematically dipole moment is given by this formula. Mu is equal to charge into distance of separation. It is measured in terms of a unit that is called as dBi unit. It is denoted by capital D, and 1 dBi is equal to 3.33 into 10 to the minus 30 cm. 1 dBi is equal to 10 to the minus 18 ESU into centimeter. So these are the different units used to express the value of 1 dBi, where C is coulomb, M is meter, and ESU is also called as electrostatic unit of charge. Suppose consider an example of a dipole moment, or an example of dipole is HCl. HCl is a molecule in which the two atoms H and Cl are chlorine, hydrogen and chlorine are held together. There is a covalent bond, sharing of electron pair takes place here. There is a difference in electronegativity forming this bond, hydrogen and chlorine. So due to the electronegative nature of chlorine, the shear electron pair is shifted towards chlorine. Therefore, chlorine is having negative charge and hydrogen is having partially positive charge denoted by delta positive. And here partial negative charge is denoted by delta negative. So in this way, there is a formation of there is a charge separation which results into the formation of dipole. The bond dipole moment is a vector quantity since it has both magnitude and direction. Following example describe the dipole moment that arises in HCl. So we have already stated that dipole moment is a vector quantity. It requires both magnitude and direction. So see here, uh, a dipole is shown with the help of this arrow. The arrow starts from electronegative, electropositive atoms and oriented towards electronegative atom. So it starts from hydrogen and it is pointed towards chlorine, that is electronegative atom. So in this way, the direction of this magnitude is explained. So it is a vector quantity. In this way, we can describe it as a vector quantity. Now consider one more example of this dipole moment, that is BeF2. Dipole moment of BeF2. A beryllium fluoride bond is polar due to the electronegative nature of fluorine. So dipole is present in this molecule. But here we have two dipole. Dipole due to the one BeF molecule and dipole due to another BeF molecule. Here we have two dipole, and two dipole, they are oriented exactly opposite to each other because molecule is linear, bond angle is 180. Therefore, we know that it is an additive property. Dipole moment is additive property. So the net dipole moment is equal to the sum of two dipole present in this molecule. That this is dipole first, this is dipole second. Since it is a vector quantity, these two dipole, they have exactly opposite directions. So net dipole moment is zero because these two dipole, they have opposite sign. Okay, so these two dipole, they get oriented exactly opposite to each other, and in this way these dipole, they get cancelled and the net dipole is equal to 0. So many time question is asked, the dipole moment is BeF2, beryllium difluoride is 0, explain. So in that case you should able to explain that the molecule is linear, uh, dipole moment is a vector quantity. These two dipoles, they are oriented exactly opposite to each other, and net dipole is the sum of these two dipole and they having opposite direction, opposite sign. Therefore, the net dipole is 0. Dipole moment in water. The dipole moment in water is non-zero because water is non-linear molecule. It is V-shaped. Therefore, it is having a dipole. It is oriented in this way. It is oriented towards oxygen because oxygen is electronegative, and the value of dipole moment in water is 1.8 dBi. So, the question may arise, uh, why the dipole moment in water is non-zero? Because water is non-linear. It is V-shaped, and it is the sum of two dipole present in water molecule. Here is some examples of some molecule and their dipole moment is given. Here, as the electronegativity increases, the dipole moment value increases. As the electronegativity difference increases, dipole moment increases. Example, HF, HCl, HBr and HI. Dipole moment also depend on the position of the substituent, that is ortho, meta and para dichlorobenzene. Okay. So this is also some example. Carbon tetrachloride dipole moment is 0 because we have 4 dipoles. They are oriented exactly opposite to each other. Okay, same thing is happening here, but in chloroform it is non-zero. Carbon tetrachloride have 0 dipole moment, while in chloroform it is non-zero because here all dipoles, they are not exactly opposite to each other, and hence the net dipole is not non-zero. Now see here we have three cases of dichlorobenzene. We know that dichlorobenzene exists in three different isomeric forms such as orthodichlorobenzene, metadichlorobenzene and paradichlorobenzene. And the dipole moments for ortho, meta and para is given. In ortho, we have the value of dipole moment is 2.4 dpi. In meta, we have the value 1.72 dpi. and in para-dichlorobenzene the value is 0 debye. In case of para-dichlorobenzene, see here we have dipole due to two CCl bond, and these two CCl bond, they are oriented exactly opposite to each other, and hence the net dipole is 0. While in case of ortho and meta, they are not oriented exactly opposite to each other, therefore the value is non-zero. Again, same way we can explain why the dipole moment in carbon monoxide is 0 and why the dipole moment in trans 1,2-dichlorobenzene is 0 while cis 1,2-dichlorobenzene is non-zero. Again, if dipole they are oriented exactly opposite to each other, then we have 0 value, we observe 0 value, and non-zero value if they are not exactly opposite to each other. So in this way, dipole moment is used to distinguish between ortho, meta and para dichlorobenzene, as well as it is used to explain cis and trans isomerism, linear and non-linear molecule. Okay, so this is the case of methane, activating and non-activating groups. So electronegativity or here we have the donating, uh, we have nitrogen, we have oxygen. So nitrogen, lone pair over nitrogen is delocalized in this benzene ring, and in this way, due to the delocalization, there is a clear-cut formation of charges which leads to increase in this dipole moment value. So the tendency of donation of lone pair is less in phenol compared to in aniline. Therefore, we have highest value of dipole moment in aniline compared to phenol, compared to anisole, and compared to plain toluene. So in this way, similarly, we have activating and deactivating group, and on the basis of activating and deactivating group, dipole moments value changes. Here again some examples, and their respective dipole moment value in debye is given. Now, dipole can be classified into different types such as permanent dipole moment and induced dipole moment. In permanent dipole moment, there is a permanent charge separation, while in induced dipole moment, initially there is absence of dipole, but when external magnetic field is applied, then there is a charge separation takes place, that is called as induced dipole. Induced dipole is also called as temporary dipoles. Okay, so this is all about two important physical properties: optical activity and dipole moment.